Hello everyone, welcome to the channel. I like read mathematics for machine learning, Mark Peter Deiser Rowe and Aldo Faisal Chen Sung On. For machine learning is the latest in a long time, in a long line of attempts to distill human knowledge and reasoning into a form that is suitable for constructing machines and engineering automated systems. As machine learning becomes more ubiquitous and its software package becomes easier to use, it is natural and desirable that the low-level technical details are abstracted away and hidden from the practitioner. However, this brings with it the danger that a practitioner becomes unaware of the design decisions and hence the limits of machine learning algorithms. The enthusiastic practitioner who is interested to learn more about the magic behind successful machine learning algorithms currently faces a daunting set of prerequisite knowledge, programming languages, and data analysis tools, large-scale computations, and associated frameworks, mathematics and statistics, and how machine learning builds on it. At universities, introductory courses machine learning tend to spend early parts of the course converting some of the prerequisites for historical reasons. Courses in machine learning tend to be taught in the computer science department, where students are often trained in the first two areas of knowledge, but not so much in mathematics and statistics. Current machine learning textbooks primarily focus on machine learning algorithms and methodologies and assume that the reader is competent in mathematics and statistics. Thereof, these books only spend one or two chapters of background mathematics, either at the beginning of the books or as appendix. We have found many people who want to delve into the foundation of specialist machine learning methods or struggle with the mathematical knowledge required to read machine learning textbooks. Having taught undergraduate and graduate courses at universities, we find that the gap between high school mathematics and the mathematical levels required to read a standard machine learning textbook is too big for many people. These books bring the mathematical foundations of basic machine learning concepts to the fore and not collect the information in a single place so that this skills gap is narrowed or even closed. Why another book on machine learning? Machine learning builds upon the language of mathematics to express concepts that seem intuitively obvious, but that are surprisingly difficult for formalize. When formalized properly, we can gain insights into the tasks we want to solve. One common complaint of students of mathematics around the globe is that the topics covered seem to have little relevance to practical problems. We believe that machine learning is an obvious and direct motivation for people to learn mathematics. This book is intended to be a guidebook to the vast mathematical literature that forms the foundation of modern machine learning. We motivate the need for mathematical concepts by directly pointing out their usefulness in the context of fundamental mathematical learning problems. In the interest of keeping the book short, many details and more advanced concepts have been left out. I keep it with the basic concepts present here and how they fit into the larger context of machine learning. The reader can find numerous resources for further study, which we provide at the end of the perspective chapters. For readers with a mathematical background, these books provide a brief but precisely stated glimpse of machine learning. In contrast to other books that focus on methods and models of machine learning, McKay 2003, Bishop 2006, Alpadin 2010, Barber 2012, Murphy 2012, Salsar and Ben David 2014, Rogers and Girolami 2016, or Programming Aspects of Machine Learning, Mueller and Guido 2016, Raskan Mirjalili 2017, Schuller and Allied 2018. We provide only four representative examples of machine learning algorithms. Instead, we focus on the mathematical concepts behind the models themselves. We hope that reader will be able to gain a deeper understanding of the basic questions in machine learning and connect practical questions arising from the use of machine learning with fundamental choices in the mathematical model. We do not aim to write a classical machine learning book. Instead, orientation is to provide the mathematical background applied to four central machine learning problems to make it easier to read other machine learning textbooks. Who is the target audience? As applications of machine learning become widespread in society, we believe that everybody should have some understanding of these underlying principles. This book is written in an academic mathematical style which enables us to be precise about the concepts behind machine learning. We encourage readers unfamiliar with this seemingly terse style to preserve and keep the goals of each topic in mind. We sprinkle comments and remarks throughout the text in the hope that this provides useful guidance with respect to the big picture. The book assumes the reader to have mathematical knowledge commonly covers in high school mathematics and physics. For example, the reader should have seen derivatives and integrals before and geometric vectors in 2 or 3 dimensions. From there, we generalize these concepts. Therefore, the target audience of the book includes undergraduate university students, evening learners, and learners participating in online machine learning courses. In analogy to music, there are three types of interacting that people have with machine learning. Astute listeners. The democratization of machine learning by the provision of open source software, online tutorials, and cloud-based tools allows users to not worry about the specifics of pipelines. Users can focus on extracting insight from data using off-the-shelf tools. This enables non-tech savvy domain experts to benefit from machine learning This is similar to listening to music. The user is able to choose and discern between different types of machine learning and benefits from it. More experienced users are like music critics, asking important questions about the application of machine learning in societies such as ethics, fairness, and privacy of the individual. We hope that this post provides a foundation for thinking about the certification and risk management of machine learning systems and allows them to use their domain expertise to build better machine learning systems. Experienced artists. Skilled practitioners of machine learning can plug and play different tools and libraries into an analysis pipeline. The stereotypical practitioner will be a data science or engineer who understands machine learning interface and their use case and is able to perform wonderful feats of prediction from data. This is similar to a virtuoso playing music where highly skilled practitioners can bring existing instruments to life and bring joy to their audience. Using the mathematics presented here as a primer, practitioners will be able to understand the benefits and limits of their favorite method and to extend and generalize existing machine learning algorithms. We hope that this will provide the impetus for more rigorous and principled development of machine learning methods. Fledgling composer. A machine learning is applied Machine learning is applied to new domains. Developers of machine learning need to develop new methods and extend existing algorithms. They are often researchers who need to understand the mathematical basis of machine learning and uncover relationships between different tasks. Hello, Walker is Godet. Hello, Anna Maya Linkiter Barrett. Number two, Jesus Carmona. Hello, everyone. Fledgling composer. A machine learning is applied to new domains. Developers of machine learning need to develop new methods and extend existing algorithms. They are often researchers who need to understand the mathematical basis of machine learning and uncover relationships between different tasks. This is similar to composer and music of music who, within the rules and structure of musical theory, create new and amazing pieces. We hope these books provide a high-level overview of other technical books. For people who want to become composers of machine learning, there is a great need in society for new researchers who are able to propose and explore novel approaches for attacking the many challenges of learning from data. Acknowledgement. We are grateful to many people who look at early draft of the book and suffer through painful exposition of concepts. We try to implement their ideas that we did not vehemently disagree with. We would like to especially acknowledge Chris, Chris Wright Weber's for this careful reading of many parts of the books and his detailed suggestion on structure and presentation. Many friends and colleagues have also been kind enough to provide their time and energy in different versions of each chapter. We have been lucky to benefit from the generosity of the online community who have suggested improvement via github.com which greatly improved the book. The following people have found bugs. proposed clarification as suggested relevant literature, either via GitHub account or personal communication. Their names are sorted alphabetical. Abdul Ghani C. Usna, Adan Geyser, etc. etc. Contribution GitHub whose real names were not listed on their GitHub profiles and data maps. We are so very grateful to Parames Ramam and the many anonymous reviewers organized by Cambridge University Press who read one or more chapters of early version of the manuscript and provide constructive critiques that lead to considerable improvement. And a special mention goes to Inesi Megi Sidra. Symbol A, B, C, alphabet, beta, lambda, scalars and lowercase. S, Y, C vectors are all lowercase, etc., etc., etc. Mathematical foundations, introduction and motivation. Machine learning is about designing algorithms that automatically extract valuable information from data. The emphasis here is on automated. Machine learning is concerned about general purpose methodologies that can be applied of many data sets while producing sometimes than in meaningful. There are three concerns that are the core of machine learning: data and model and learning. Science. Machine learning is inherently data driven. Data is at the core of machine learning. The goal of machine learning is to design general purpose methodologies to extract valuable patterns from data, ideally without much domain specific expertise, for example, given a large corpus of documents. Some libraries. Machine learning methods can be used to automatically find relevant topics that are shared across documents. Example goes and menu libraries. Machine learning methods can be used to automatically find relevant topics that are shared across documents. Hoffman, all 2010. To achieve this goal, we design models that are typically related to the process that generates data similar to the data set we are given. For example, in a regression setting, the model will describe a function that makes inputs to reveal real value outputs. To paraphrase Mitchell 1996, a mobile model is said to learn from data. Its performance of a given task improves after the data is taken into account. The goal is to find good models that generalize well to yet unseen data, which we may care about in the future. Learning can be understood as a way to automatically find patterns and structuring data by optimizing the parameters of the model. While machine learning has seen many success stories and software is readily available to design and train rich and flexible machine learning systems, we believe that the mathematical foundation of machine learning are important in order to understand fundamental principles upon which more complicated machine learning systems are built. Understanding this principle can facilitate creating new machine learning solutions. training and debugging existing approaches and learning about the inherent assumptions and limitation of the methodologies we are working with, finding words for intuitions. The challenge we find regularly in machine learning is that concepts are slippery, and a particular component of the machine learning system can be abstracted to different mathematical concepts. For example, the word algorithm is used in at least two different senses in the context of machine learning. In the first sense, we use a phrase machine learning algorithm to mean a system that makes predictions based on input data. We refer to these algorithms as predictors. In the second sense, we use the exact same phrase machine learning algorithm to mean a system that adds some internal parameters of the predictors to that it perform well or future unsense input data. Keywords refer to this adaptation of training a system. This book will not resolve the issue of ambiguity, but we want to highlight up from that depending on the context, the same expressions can mean different things. However, we attempt to make the context sufficiently clear to reduce the level of ambiguity. The first parts of this book introduce the mathematical concepts and foundations needed to talk about the three main components of machine learning system, data models and learning. We will briefly outline these components here, and we will revisit them again in chapter 8 once we have discussed the necessary mathematical concepts. While not all data is numerical, it is often useful to consider data in a number format. In this book, we assume that data has already been appropriately converted into numerical presentations suitable for reading into a computer program. Thereof, we think of data as vectors as another illustration of how subtle words are. There are at least three different ways to think about vectors. Vectors as an array of numbers, a computer science view. Vector as a row with a direction and magnitude of its view, and a vector as an object that obeys additions, scaling a mathematical view. A model is typically used to describe a process to generating data similar to the data and thereof got models and also be true of a simple version of the real node data generating process, capturing aspects that are relevant for modeling the data and extracting hidden patterns from it. A good model can then be used to predict what will happen in the real world without performing real world experiments. We, we now come to the crux of the matter, the learning component of machine learning. Assume we are given a dataset and a suitable model. Training the models means to use the data available to optimize some parameters of the models with respect to a utility function that evaluates how well the model predicts the training data. Most training methods can be through of approach nose to climbing a hill to reach its peaks. In this analogy, to peak of the hill corresponding to a maximum of some desired performance measure. However, in practice, we are interested in the model to perform well using data, performing well on data that we have already seen. Training data may only mean that we found a good way to memorize the data. However, this may not generalize. well to use and data, and in practical application we often need to expose our machine learning system to situations that it has not encountered before. Let's also summarize the main concepts of machine learning that we cover in this post. We present data as vectors, which shows an appropriately model, either using the probabilistic or optimization view. Okay, goodbye.